Okay, thank you everyone, whoever is here. I know this is the last session, so we have been at it for the last 3 days. Hopefully in the next 30, 40 minutes, you get to hear something interesting from this talk. We are tackling a specific use case, but I believe there are other use of these stuff that we are going to show here. I do want to call out Manoj, who is the one of the contributors to this paper. Unfortunately, he couldn't be here today. Also, I'm Dishankar. I'm a distinguished technologist with HP, and I have Nutan, my colleague here, who's an architect. So today we are going to talk about basically, using some of the GenAI techniques to show you how we have used graph databases, which we are using for knowledge bases to enhance defect triaging and issues, investigating in a storage system. Okay, and we are, like I said, tackling a particular use case. But if you see, there are other usage of this, and I believe that when you go through the way we have kind of created the stuff and how we have built the graphs, you will come up with new ideas that you will see. Okay. Moving on. So for the last 3 days, we have been basically talking about a lot of generative AI areas that various people have given talks on. So today we are going to talk about like I said, the graph databases and how we are using that for enhanced context and accuracy through RAG use cases, as well as deeper understanding and reasoning through some of the semantic searches and inferences that we draw out of that. And I'm going to talk about the abstract, describe the problem statement, some of the limitations that we have in our current systems. Then I'm going to hand it over to Nutan. He's going to explain what the solution is, what are the different building blocks, the overall architecture, and then we'll take you through an example that we have run and how we have created the graph, and how eventually we walk through that and come up with the results. Okay. So in this slide, as it outlines, right, our work isn't, debugging in a storage system is not as simple as debugging a typical SaaS application, right? Storage stacks are unique. We have different layers, and the physical hardware itself creates, layers of complexity. And when you're trying to untangle, logging, concurrency, and control flow, it's massive, right? The result of this complexity is, we get a lot of noisy, interleaved system traces that are incredibly hard to debug, right? And this is where the traditional AI tracking, right, which are trained on general purpose code, right, they fail because they have the content, but they do not have the context, right? And so the key innovation that we are going after here is basically start treating AI as an insider, okay? We purposefully augment our system with knowledge extracted directly from a source that we trust, which is our functional tests. These are not just code, right? So these represent our understanding of how the system will behave in a realistic end-to-end scenario. Now, by transforming this intent into structured knowledge graphs, and you will see this in subsequent slides, we give AI the insider context that it needs to truly integrate in order to understand the end-to-end debugging. Now, before we dive into the details, let's spend a little bit of time on what the problem we are against, right? So as you can see, right, there are 3-4 areas, right? One is, I talked about the multi-layered complexity where a single failure can repel through multiple layers of hardware, firmware, different software stacks. And diagnosing a concurrency issue in the environment, it's not just hard, it's a nightmare, right? And you really need a lot of system knowledge in order to kind of stack together end-to-end scenarios, right? The second thing that it manifests is log correlation chaos, right? Where the image of the engineer here is quite relatable, right? So you are faced with a lot of non-transactional interleaved mess of log from different sources, right? And the critical failure signature you're looking at is there, but it is buried under a lot of noise and a lot of other things that you have to shift through in order to make a total understanding. So as you guys are aware, right, so typically 80% of our time, and this internal matrix as well shows that, is really spent in debugging a problem and understanding the problem. It is not even fixing it, right? And most times what we have seen is, it is some of those handful of senior engineers who are always given those critical problems to solve because they are the ones who can stitch things end to end. And this is also where, as some of you would relate, it's very hard to get somebody new into the stack or into the code where they can quickly become productive and start figuring out what's going on when you throw a new problem at them, right? And this is what we are trying to solve, okay? So there are some limitations with some of the solutions that we have today. The first is, we talked about the knowledge quality, right? So the system is as good as the knowledge you give it, right? So if you are feeding it inaccurate data, it's going to cascade through the systems, right? Then you have some of these log pattern changing, right? Because you will have new stuff come out, some of your existing alerts will become obsolete, and you will add new stuff, new alerts, new messages, and you have to continuously build on that so that the information and the accuracy do not decay over time, right? And then you of course have, this people have talked about in length, that you cannot throw all the logs, all the stuff at a large language model, right? It has its own limitations, and if it cannot get the full context, right, it is going to give you inaccurate and wrong diagnosis of a problem, right? So there are two undesirable outcomes of that, right? So one is false positives that we will see, although something is actually passing or working fine, it will flag and it will basically create noise in the system. And the second thing is, if you throw a new problem at a model, right, if it doesn't have that background, right, it is really hard for it to make sense out of it from scratch, right? Now with that, let's move to the architecture of the system and some of the other details that Nutan is going to cover.
Hello. Thanks, Dishankar, for setting the context and the problem we are going after. So, I'm Nutan Prasad from Hewlett-Packard Enterprise, HPE. I will walk you through on how we are approaching to solve this problem. Given a problem, we wanted to see how the AI technologies like LLM model, RAG, and the agentic approach could help us to triage a test failure in a storage system. Here is the high-level block diagram where we highlight the input and what is the core of the innovation and then what we are expecting out of the solution. As you could see, the user input could be in multiple ways. It could be like a chatbot experience where you ask Q&A and get some insights about it. Or it could be a specific query related to the function or specific scenarios. The idea here is to build a knowledge graph with the storage system code and in conjunction with the functional test. The core idea of our innovation is how we are building this knowledge graph using the graph database to render the relevant documents based on the query. As you could see, our solution is also equipped with a knowledge builder agent, log agent, and the code RAG. This is a multi-agent system that's going to help us in triaging the test failures. Again, this is at a very high level. I'll be talking in detail as we go through the slides. Now, let's talk about the technical infrastructure and the various components that are involved in the solution. To start with, we have privately hosted a LLM model in our infrastructure. We don't want it to depend on external APIs for interacting with the model. And we have deployed these LLM model using the transformers libraries. This gives us a control on security, performance, and also the customization. It's very critical for an enterprise storage system where the data privacy matters a lot. So that's where the model having locally is going to really help. Now, there are various models that we have used in this use case. So each model is designed for a specific purpose, like Llama, Qwen3B, ChatGPT, right? there are some purpose that the models are designed for and the data that it is trained for. We use a coder model to understand the code. We use summarizer model to understand the functional test spec and what the functional test is all about. We also have a open API compatible server to interact with the model. You could think of it like an interface between the application and the model where you could interact with the model to get some responses or the interactions. This also makes it easier for other components, agents, and the applications that we have in-house. Alongside the LLM, we also have embedding models. Again, these embedding models are also locally deployed. These embedding models is what we use to convert the code, functions, and the integration test into something meaningful. It's pretty much essential to capture the meaning rather than just the keyword, right? That's where this embedding is going to help us. Now, with the embedding, we can perform similarity search to render the relevant documents based on the query. Once the embedding is all done, we need a place to store and query these semantic vectors. Again, these vectors, the size of the vectors depends on the model, what we use. It could be 1024 or 1551. It all depends on the model that we are using. Once you have this embedding generated, we need a place to store and query them. That's where the vector database comes into picture. With embedding, this also helps us to retrieve the most relevant code snippets, logs, test cases, and also also it is optimized to handle the scale. And the scale that we are talking about is millions of records in case of vector database. Now that we have a foundation set, let's try to understand how are we even parsing this code. The code is very complicated, right? Each programming language has its own constructs. In case of C, it could be like structures, functions, pointers, and so on, right? How do you understand? Can model directly understand the code? Yes, of course, models can understand the language, but it's always easier to extract these code and functions in a structured way. So that is where we are using the AST-based chunking so that when we extract the code from the storage system or the integration test, we still maintain the structure of the code. Instead of just splitting the code in terms of lines or in terms of keywords, we try to maintain the structure as it is. Now again, if we talk about the code or a function, it's up to a developer where he would have added more comments, made it more readable, or you would have added more function docs to understand what the function is designed for. Can we just derive what this function is all about just with the code? Yes and no both, right? So that's where we use model to also generate more insights about the function, like what the function is intended to do, and what scenarios as the function is handling given a test as a context. Now, once we have the code parsed in a logical segments like functions, classes, and the structure of the code is well maintained, we parse this code and convert it into embedding. Now, do I need to embed everything? No. We can decide what is that we wanted to embed in this code segments or the meaningful logical segments. Once we have this code parsed, we make use of rack system to retrieve the most relevant code chunks for a given query. There are two main approaches you could use to make the model understand about the customer-specific data or the domain-specific data. One approach is fine-tuning. Fine-tuning a model with a new set of data so that model memorizes and understands what the question is all about. There could be some internal technologies or the components, like for example, we call it as integration. In the industry, it calls it functional. So there are some terminologies which is specific to the company, and the model doesn't understand because the model only has the real world knowledge, not the domain knowledge. So that's where the RAG comes into picture. RAG is a retrieval augmented generation. So with the RAG, we keep the model as it is and try to extract the relevant documents, build the right set of context, and provide that context to the model at a query time. Again, every model has a limit on the context. Can it handle everything? No. And can we feed unlimited data to the model? Of course not, right? So that's where the context engineering becomes very, very critical. Every model has a limit on the context, and also this context that we are building, if it is not very relevant to the query, then the answer is also not that great, right? So the response from the model always depends on the knowledge that the model is aware of. In terms of real world knowledge, yes, it could use real world knowledge and answer. In case of domain, you have to render the relevant documents and give it to the model so that the model can respond based on the query. Now, the success of the RAG in our solution depends on how we are building this data and how we are structuring this data before talking to the model. Now that we understand how the code is parsed, extracted, now let's try to understand how we can make use of LLM model to generate more insights about the function or a functional test. This is where this is what we call it as insights, right? Insights could be like, okay, have a function. What is this function used for? And what is the intent of this function? Can I derive some insights about, okay, what are the scenarios that this function is handling given a test, right? So the function, the nature of the function and the behavior of the function changes based on the test. Now, specifically, we wanted to understand each function and its behavior and how that function is related to the functional test. Now, we also capture the behavior of the function, the parameters, and the state of the function before and after the function is executed. The idea here is to capture the complete call graph of a function and what functions are executed in the same workflow. Also, it's very essential to understand what are the various scenarios as part of functional test is executed in this functional context. This also gives us a pointers on the functional coverage of the code. Now, our goal, moving on to the next is, our goal is to build a comprehensive function profile, like the function insights, but it doesn't make sense if you are trying to extract the insights and the scenarios based on one single test. That's where we try to run multiple tests to understand the behavior of the function and the nature of the function through multiple tests and layer them together. This is how we get the deeper view of a function and how it behaves across different situations. While we are extracting and processing the code in conjunction with the integration test, we also try to capture the happy path, non-happy path, and how the error handling is handled and how failures are managed with various workload and system configuration. Together, this gives the overall function's correctness, resiliency, and efficiency. Now let's dive into the knowledge graph. We have heard a lot about knowledge graph. Now let's try to understand what the knowledge graph is all about and how are we building this. So to build this knowledge graph, we use Neo4j graph database. Graph database is a type of a database that stores and manages data in terms of nodes and edges, where each node represents the entity or an object. But when it comes to edges, the edges is what represents the relationship between these nodes. So the current solution, the relationship that we have supported is covers and the calls. Now, this relationship could be used between the tests, like one test covering another test, or one test calling another function, or a function calling another function. As I have highlighted in this graph, so the ones which are on the top and highlighted in yellow is all our functional test. This is in conjunction with the storage system code. And the root nodes is going to be the functional test, and the leaf nodes is what could be a other test or the functional code. Now, when it comes to the functions, the ones which are highlighted in orange is the functions that are shared between multiple tests. So if there is an impact in, like for example here in the slide, setup replication, then the impact is on both the test high availability and also the basic replication. So this also helps us to understand the impact of one failure over other test cases. Now, let's try to understand this knowledge graph in detail. The leaf nodes that we have, the way we build this is, we run the functional test and try to capture the entire stack and the entire flow of this functional test. So that way, given a test, we understand what the workflow is and what are the various functions and the scenarios has been covered in this execution path. In this example, for simplicity, I'm tagging each node with just the function name, but this is not reality. In reality, each node that we have, we capture more insights about the function. And this data comes from two places. One is the actual code. It could be a system code or the integration test code or the functional test code, right? The other data comes from the model. We infer and extract and generate these insights based on the scenario. And in this example, I've just captured 3 to 4 test details. But in reality, this knowledge graph will be in thousands, millions, based on the number of integration tests or the functional tests you have, and then the functions that you are covering as part of that test. This is one such example. Like, what is that you are trying to capture? This is what we call it as a context, right? Now, given a function, given a query, the model would respond based on that code. Now, along with the code, can we extract more and more details about the function? Like for example, the node data structure is for a function called allocate storage. Similarly, we also build the rich data for the functional test. And this node data is what consists of function, the path of the function, and the whole function body, and the various scenarios that this function is executed in terms of API path, and how the error handling is handled, and in the various configuration and the performance metrics, if there are any scenarios that are specific to this function, is all captured as part of the node data. This is the detailed architecture of our solution, and it kind of puts everything together that we discussed so far. On the top, the system code and the integration test. I would like to explain this architecture in 3 stages. The first stage is what I refer it to as ingestion. Currently, there is nothing in the knowledge graph. Now, how do I start building this knowledge graph? With the system code and the integration test, we start processing each and every function that is there in the system code to understand what the function is, what the intent is, and what are the scenarios that this function is capturing. And everything related to the system code is what we parse and process using the AST semantic parser. And this data is the raw code that we extracted from the code base. Then we run this code into a prompt engine. We have a predefined prompts like in the previous slide, the way I explained, and the data that the insights that we extracted out of the function is all the predefined prompts that we have. So with this predefined prompts, given a function, we try to extract more and more details about the function in conjunction with the test. And can LLM model generate the rich context in one single query? No. That is where we have the insights builder to use multiple predefined prompts to extract more and more data from the code, and we build that code block. Once we have this code block, we try to embed the data and then store it to the vector database. Now, we saw a node structure consists of multiple fields. Do I need to embed everything, right? So that is a bit tricky. Should I embed just the function code? Or should I embed just the scenarios? Or should I just embed the natural language summary of the function? So what we did is we tried to create a composite key based on what are the fields that will be helpful in a user query. So based on that query, we tried to create a composite key and then generated all the data as part of that field. And that is the field we use for embedding and storing that data into the vector database. Now, the next stage is knowledge graph. Now, I have the code processed. The code is there. The additional insights is there. Now, how is this code playing a role in a functional test? So that's where the knowledge graph building comes into picture. So what we use is we have a test execution engine which runs all the functional tests and with all the logging enabled with the various configuration and the performance considerations. We run all the tests to capture the call stack, the call flow, to build this comprehensive information about the overall execution path. And we capture this data, and once the test is run, we have two things. Along the test, we have the test case logs and then the array logs. That is where the real challenge is. Now, when it comes to a test, as soon as the test is run, there is a control path logs, there's a data path logs, and the application logs, kernel logs, NVF. There are multiple other logs that we see to triage a problem. So what the log analysis agent does is, we try to build that knowledge. Okay, what is the test case that was executed, and what is the time the test case execution started, and also note if there are any failures. So that failure time is what we use to correlate and understand what the test case is and what the logs, storage array logs are talking about. This log analysis agent is a multi-agent system which talks to a code rack to understand, okay, here is the test case, here are the multiple steps that I had run as part of this test, and given the code context, we'll try to extract the scenarios that it is trying to run, and then we build the knowledge graph using the call stack. For each integration test, we derive what are the functions that are involved in the execution path, and that helps us to build the knowledge graph, and that is where we call that as nodes. And the third stage is,
so how much of this did you do manually, and how much of this did you do by putting them into a machine and grinding?
the question is, how much did we do this manually and how much we used model, right?
Sure.
So like I mentioned, the code and integration test, the raw code is coming from the code. And the insights, scenarios, what scenarios it's trying to come up, is executing in the path is all generated by the model. So there is no human in the loop who is generating this. And for every test that we have a predefined prompts that runs as part of the multi-agent system to extract more and more insights about, okay, given a function, can I get the call stack? Given a function, can I extract what are the different tests that is run? And what is the test suite this test is running?
Basically mapping the end-to-end use case that we are trying to approach with that test. That's how you build that, okay, for this use case, the graph that he showed, what else is also getting called as part of that, that's the whole build out, basically.
Yeah. So with this data, we try to build knowledge graph. And this knowledge graph that we build, when we run one test, it's going to capture the test and also the functions that are involved in this test. Not with a single test, can single test covers all the scenarios in the function? No. That is where the multiple test execution helps us to build the quality knowledge graph.
So in our system, we ran about 1,200 tests in order to build the data, just as an example.
And this is an example, this is a simple example I wanted to take to demonstrate how the knowledge graph looks like. So here the test case that has failed is test availability failure. And the reason for the failure is replication setup failed. Along with the test, we also have test logs and also the array logs. Once there is a failure with the two data sets, at what time the test was run and what time the failure was reported. So based on this, we try to do we pick the time relevance window. And this number depends on the test case to test. For now, we have defaulted it to 10 minutes, but eventually we wanted to derive based on the scenarios. Now, we start with the 10 minutes, we extract the logs from the test and then extract the logs from the storage array and then give it to the model. So can we give the logs, the 10 minutes is a lot where it tries to generate a massive amount of logs. We cannot give logs as it is. That's where we do log clustering. So with the log clustering, for the system where the test case has failed, this log clustering is going to help us to understand what is noise and what is an anomaly. So how do we build this is, we use drain tree clustering approach to build that tree of what are the log lines that's appearing in the storage array and how frequently those log lines are appearing. So based on the cluster size, we can decide what is anomaly and what is not an anomaly. So we pick those anomalies, and that anomalies is what goes to the agent. Now, agent has these anomalies, and the queries that hits onto the pre-built knowledge graph is based on these anomalies and the log patterns. Now, the knowledge graph that we have, the Neo4j graph database supports two kinds of query. One is a normal query, the other one is a semantic query. The normal query is, given a test, given a function, what other functions or what other tests are covered. Given a function, what other function is covered. And the other kind of query is a semantic query. This is the reason why we choose graph database. Now, this is an example for the same test failure. Now, with the failure, we know where exactly the failure is and what is the log anomaly. With the log anomaly and the patterns, we try to locate we try to locate the node or the function or the code path which matches this log anomaly. Again, this is based on the cosine similarity. We apply cosine similarity to find the matching node. The best part of graph database is once you find the matching node, you have an option to traverse upward or downward. Now, you found a matching node. In this example, allocate storage. Allocate storage is a matching node based on the cosine similarity. So now, can I derive the root cause or the probable cause just by looking at the allocate storage? No. So we need that entire stack. With graph database, you have an option to extract what data is required from your root and parent nodes. So from the context that I showed, along with the function body, we extract certain fields related to the test scenarios and what scenarios is executed in this path to derive the failure pattern and also the probable cause. The current system that we have designed and working is able to detect the failure pattern and also suggest the probable cause. This is our first step. Going forward, we wanted to see, you know the failure pattern, you know the probable cause, can I optimize the context further instead of me feeding the summary of the test case and what is the code path, and also try to see if we can get the probable fix for this problem. That is where we are heading to. In this knowledge graph, you can also see the ones which are highlighted is indicating the failure path. And another node which is marked purple, the basic, in this example, the basic replication is also impacted because there was a shared node that was used in the failed path. The high availability test is also making use of setup replication, and the basic replication is also making use of setup replication. Unless it is an environmental problem or something related to the environment, the impact of the failure will be there in multiple tests. So this way you could also derive what is the impact of any failure in the storage system. Here are some of the benefits with the solution that we have. The one solution, of course, is a significant time savings in triage process. And if the same process is hooked on to the pipeline, I believe all the storage systems have the functional test and we run based on some periodicity, like a daily or a weekly. As soon as there is a test failures, our system, the multi-agent system, kinds of kicks in based on the failure, try to understand what the failure is and what scenarios is failing and how this is going to impact multiple other tests with the detailed analysis. So this is going to help the developer as the initial triage nodes. Because when the developer starts debugging a problem, he would start from the test. Okay, what is the test that it was run? What scenario was experimented? Where is the failure? And then he'll have to look at the massive amount of logs to figure out where the actual root cause is. With this knowledge graph, you can clearly identify which function had a problem given the scenario and see what is the probable fix. And this also enhances the left shift. If we integrate the knowledge graph mechanism or the agentic system that we have into the PR process, we detect the problem much earlier before even hitting the system. So that for every code change that the developer makes, we run this test to understand what is the impact if there are any issues that the developer is inducing into the system. And like I mentioned, these are all APIs. It's not an application where the user has to get into the application and start giving some Q&A questions and expecting some answers. These APIs can be plugged into a chatbot system to make a generalist into a specialist. Because I generally take this intern analogy. With the intern coming in, joining a team, and if he wants to understand what is a code or what is the kind of test that we run in a component like remote copy or a data protection, this knowledge graph is going to help him to understand, okay, what is a code path, what are the different tests that are available, and if there is a scope for him to enhance or implement new test cases based on this existing knowledge. This also, as we pick up the new features for every release, it also helps us to create the test plan with what the change is, what is the new feature, which area of the storage product we are introducing this new feature, and what are the existing tests and the functionalities that we have and the various scenarios that we are carrying, and can we enhance existing tests or can we create a new plan. So this also helps us in the test plan. With that, I would like to wrap up on a note that with this solution, we are trying to transform a traditional debugging approach into a multi-agentic system with the knowledge from functional test and also the code base. Thank you everyone for attending our session.
Thank you.
Any questions?
Go ahead. Go ahead. Sorry.
The knowledge graph's accuracy, right? So as I go through the development process, it starts with a very mature code and then you have tens of developers, right? Is this looking into some previous reference and then building a baseline and improving over
Yes.
time?
Yes.
Or
Yes.
see, like, I'm trying to understand when did you discuss this? Is it early development or towards the very end?
Yeah. So if you look at this slide, we started this approach with the current code. So the current code, the storage system code, and also the test, both are available. With the current system, we try to build the system. As we go through the new set of features, we try to enhance the existing knowledge graph.
So current results, based on the stuff that we have done so far, so we are concentrating on some specific areas. So we have seen about 75 to 80% accuracy, and like I said, right, we are feeding that back, right? We are trying to improve that over time. The other thing that we have not talked about is you also have this defect that have been fixed, right? That data is also with us, right? What are the areas of code that we have had issues, what we have fixed. So that is also part of the knowledge that we are trying to get to, right? So over time, if the system is looking into similar areas and all, it can quickly go and say that, oh, I've seen this before. Okay, this is how I fixed it, right? Okay.
So you mentioned earlier, like you have abnormal logs and then map it into the product search. So is it also because of the log message as appeared in the code? Or how do you actually, like you mentioned about normal logs and then map it to code?
So the question is, how do we determine what is anomaly versus what is normal?
And also how do you map it to the code?
Yeah. So the first part of the answer is, you are also making the test run on happy path, right? So you know the logs that you're supposed to see when the stuff works, right? And then you have the same test which is failing, and you know that these are the anomalies that I'm seeing, right? And then how the way we have built it, right? For each of the functions, we know what is the path, right? So you can actually from that anomaly go directly into the the code path and look at what are the log messages that are being printed and get to that specific area to figure out what's going on. So that's how we are mapping it.
And this data, I would like to add to the logs part. So how we are able to directly correlate from logs to what function. So we look at the coverage data. So given a functional test, what are the list of functions that are involved in this flow? So that data we already have. So with that data and the logs, we closely correlate based on the similarity search. So we don't have to do 1:1 map. Like for example, the names of the volume or the port, we don't have to look at those variables. What we are doing is just a similarity search to see, hey, here is a pattern. Can I find any function as a similar pattern? And when we query this, you are based on the request, you get multiple records. Like general similarity search, you can always control the number of records that you want to get from the vector database. So what we do is we extract the records from the vector database and apply a re-ranking algorithm.
Yeah, that's a good point.
So this re-ranking model is what helps us, okay, here is a prompt, here is a document. Is this document very relevant to this? If not, then we try to use C-scope. Okay, so the C-scope is our backup plan. Okay, here is a function, what is the path? What are the other call chain that are involved in this code flow?
Good.
So this took some time and engineering time to set up before you were able to run it against currently running tests and start to get results from it. How much engineering effort went into setting this up?
That's a very good question.
Let's repeat the question. So basically, the question is how much engineering time did we spend to set this up?
Yeah. There are two parts. One is the model setup, right? What models you want to use, what OpenAPI compatible server you want to use. Do you want to use open source, or do you want to use something that is existing like VLLM or Olama, right?
So just putting it all together, how long did it take?
Yeah. So we have, like Dishankar mentioned, we have close to 12,000 tests. And this, for the 12,000 plus tests, we closely took, per functional test, we took 20 minutes. So close to a month and so to fine tune these data and extract it into the knowledge base.
By the way, as all of us are also, figuring out, there is a lot of skepticism, right? So you cannot have a lot of people getting involved because then it will not work and all that thing happens, right? So you always start small with 3-4 people, you try to get this done and then prove the point, right? So that's how we have also, targeted.
Yeah.
I think.
So it took about 1 man month.
1 month.
Yeah.
Yeah. And also the analysis part is an iterative process. It depends on the model confidence.
Yeah, so
right?
that's the other part, right? I mean, it is a continuous process, right?
So there was time afterwards.
Yes, absolutely.
Right. Like for example, I have a log, I have a model, first iteration, it extracts something, okay, it finds out something. So that's where the agentic approach is all about, right? So you find something, do you want to stop or do you want to run in the loop? You use multiple tools, extract more insights, okay, again, reevaluate the system, see how confident you are. So current threshold that we have set for the model accuracy is 80%. If the model is confident about the root cause and the probable cause up till 80%, then we stop. That's the exit criteria for the model. Any questions?
Yeah.
So you mentioned having to track the call stack for functions, and you also have these references like Python and C code. I'm trying to how you did the correlation there. Like if I send one thing you've seen with doing code coverage, if I send an SMB packet to a server, how do I know which went to that request versus what's just running the system?
Yeah, so the question is how do we correlate the different code parts that we are traversing. So our tests are written in Python and the code is in C. So we actually use code coverage data, build Zybul, build, and you basically see for that test what all function got covered, what are the functional blocks, what are the conditional blocks. So that is what we are feeding.
Yeah, and also this AST is not specific to one language. You have Python AST parsers, C AST parsers. So based on your the language that's used, you could choose what AST-based chunking you want to use to extract the code. Any questions?
Good.
There's still kind of extent. There's cross-program calling, and there's some weirdness there that maybe, I don't know if you capture it.
So far, like I said, right, the accuracy is, that's why, we are looking at about 75% accuracy. But like I said, over time, you will get better because you are putting that feedback loop in, right? And the other thing that I mentioned, right, we are also looking into these bug fixes that the development team are doing, right? So that's another knowledge database that we have not shown here, but that's happening, right?
Yeah, and also we are trying to leverage the model's capability here. If you could see here, the code, the actual function block is also there. The model can understand C, and model can also understand Python. So this is the reason I was talking to you about the model card, how you decide the model based on the purpose. For this purpose, we have used a coder model.
Okay, I think time's up. Thank you very much.
Thank you everyone for attending our session.